So we're trying to answer this question of how did the solar system form. We've taken the first couple of steps of collecting empirical data about the solar system and then also drawing on prior knowledge, general knowledge about space and matter in general. We talked about the interstellar medium that fills space, about the different types of nebulae, and how stars can only form in dark nebulae. And we also mentioned aspects of kinetic molecular theory, which is our basic theory of how matter interacts with energy. What we're going to do now is we're going to try to put all that together and use deductive reasoning to come up with a hypothesis, a tentative answer to this question of how did the solar system form. What we're doing basically is we're trying to come up with an antecedent that's, when it's plugged into a deductive argument, gives us all of these as consequence, logical consequence of our hypothesis. Now, the antecedent is not going to be a simple statement like in our discussions about logical reasoning. It's going to be a very complex story to give us all of these consequences. But let's take a look at the hypothesis that scientists came up with. It's called the nebular hypothesis because the idea is that the Earth, the sun, the entire solar system formed from one of these nebulae. Remember, it would have to be a dark nebula. Those are the ones that are cold enough that the particles are moving slowly enough that gravity can cause them to contract. But the details of the nebular hypothesis in outline are as follows. 5 billion years ago, if you were in this region of space, you would not see a solar system. You would be in the midst of a dark nebula, which today we call the solar nebula because it's the one that we believe gave rise to our solar system. This nebula was slowly rotating in space. We don't need to explain why it was rotating. That seems to be a basic fact of the universe, that almost everything in the universe, perhaps the entire universe itself, is rotating. But we can ask questions about that rotation. What direction was it rotating in? Well, we believe it was rotating in a prograde direction. Remember, that means that if you were looking at it from above, it would be rotating in a counterclockwise direction. How do we know that it was rotating in a prograde direction? Because if it was doing that, then that would explain all the prograde motion that we see in our solar system today. We now have an explanation for why everything, almost everything, is moving in that prograde direction, because they all inherited the original motion of the solar nebula. This simple hypothesis gives us an explanation for all of that prograde motion. What we will still need to explain then are those few exceptions, but this explains almost all of the motion in the present day solar system. Now, gravity acted on this nebula. Remember that a nebula is typically about 10 light years across. Our solar system is only 3 light years across. So if the solar nebula became the solar system, it had to shrink. What can pull all that matter together into a smaller space? That would be the gravitational force. And so this shrinking is called the gravitational collapse of the nebula. This would have a number of effects on the nebula. For one thing, the rotation of the nebula would speed up. That's the result of a basic scientific principle called conservation of angular momentum. If you're doing physics, you may have already talked about this in your class, but very basically, when any object is spinning, it has this property called angular momentum, and that angular momentum depends, amongst other things, on the size of the object and the speed of rotation. And the idea of conservation means that it's kept the same. The total angular momentum of a spinning object always stays the same unless something adds to it, speeds it up, or slows it down. But that means that as this nebula contracted, Because the size got smaller, to keep the angular momentum the same, the speed had to become greater. We see this when, if you've ever watched a figure skater going into a spin, and she starts out with her arms spread out and she's rotating pretty slowly. And as she pulls her arms in closer to her body, she spins faster and faster and faster. She's not speeding herself up, she's just taking advantage of the law of conservation of angular momentum. Now, the the rotating nebula also shrank, it would also flatten out into what we call a protoplanetary disk, or a proplit. Proto means first or early. And this again is not something that we need a particular explanation for. A spinning nebula that is shrinking will flatten out. And why is that? It has to do with the balance of forces inside the nebula. So the red arrows here are showing gravity pulling the nebula inwards, and it's pulling it in with the same strength in all directions because it's the same gravity from the same matter. And so if this were all that was going on in the nebula, if the nebula weren't spinning, then this nebula would form into a spherical object, a round ball. But in fact, the nebula is spinning, and so that gives it an outward force in the plane of rotation that we call centrifugal force. This is the force you feel if you're in a car and it goes rapidly around a curve and you feel yourself thrown outwards away from the direction of the curve. The same thing happens to the matter in the nebula in the plane of rotation. So matter will get forced out this way and this way, but it will not get forced out this way or this way because the nebula is spinning in this plane. So that means that the outward centrifugal force in the plane of rotation cancels out some of the inward gravitational force here, but doesn't cancel it out in the up or down direction. So gravity will squeeze harder from the top and bottom than it does from the sides, and the nebula, as it shrinks, will end up flattening out. So here we have an explanation for a bunch of features that we saw of the solar system. The size of it, how could a solar system of 3 light years begin as a nebula of 10 light years? Well, gravity would pull it together. We have an explanation for its flatness. As the rotating nebula shrank, it would flatten out in the same way that you can make a pizza by taking round dough and throwing it up in the air and spinning it. And it also explains the prograde motion of our objects in the solar system today, because that's left over from the original prograde motion of the solar nebula.